How do we use SLURM to launch an OpenMP job? An OpenMP job runs on a single node but uses multi-threading and gets speed up by running threads in parallel on different CPU cores. For example, each compute node on Faster has two 32-core Intel CPUs, so an OpenMP job can have up to 64 simultaneous threads doing different things, depending on the problem the OpenMP program is solving. Since we've already connected to Texas A&M's Faster cluster, changed directory to the Demos folder, and entered the ls command, we know that the Demos folder contains several subfolders, including OpenMP. I can then use the cd command to change my location within the directory structure to the OpenMP folder. I can view the contents of this folder using the ls command. There I see several things, including files named 16-script.slurm, makefile, omphello.c. The source file omphello.c is a simple OpenMP program that generates some initial output, spawns threads, has each thread display a greeting that includes its thread ID number and how many threads there are, and finally generates some closing user feedback. Before we can run the program, we must build it from its source file. Unix family systems provide a utility to simplify this task named make. The details of using make are beyond the scope of this demo, but the file named makefile coordinates the build. So with a makefile in the project folder, I can in theory build my program just by entering make. But when I do so, I get an error. If I examine the output, this makefile tries to build my program using Intel's ICX compiler. It does not find it, and so generates a command not found error. I contacted the Faster help desk team. They told me that ICX is stored in the Intel/2023B module. So I can load that module by entering module load Intel/2023B. With the required module loaded, I can rerun make, and after a delay, my program will build without any errors or warnings. If I enter ls again, I see that now I have a new file named omphello, shown in green here. This file is my runnable program. To run it, we will use the file 16-script.slurm, which is a SLURM job request script. If you want, you can have multiple SLURM scripts in the same folder. I like to code the number of threads into the script's name to indicate what it is requesting, but you can choose any name. We can view its contents using the cat command. Press enter. Inside we see the shebang, followed by our various SBatch options. For the job name, we use our program's name, omphello. Next, we specify 5 seconds as its maximum runtime. This is a very short program. Even 5 seconds is overkill. Since this is an OpenMP program, we request one node, one process, and since we're going to be running with 16 threads, 16 CPUs or cores. We specify a minimal amount of memory, 1 GB in this case. We tell SLURM to stow the results in a file named slurm dash followed by the job number and then a .out. We then tell SLURM to use its CPU partition. We're not requesting very many resources, so SLURM should quickly schedule our program to run. If that were not the case, I would edit this file to activate these mail-related options. To enable any of them, I would need to delete one of these hashtags at the beginning of the sbatch command. Having two hashtags makes this a comment. Our program depends on the Intel libraries, so we load the same module we loaded previously in order to run the program. Last, we tell SLURM how to run our program. For OpenMP programs, this consists of setting the environment variable omp_num_threads to the number of cores we requested previously, 16 in this case, followed by the name of our program. We put a // at the beginning to tell SLURM to find our program in the current folder or directory. You can also specify any command line arguments your program requires here at the end. Our simple program doesn't need any. We can then ask SLURM to run our program using the sbatch command. Press enter. SLURM responds with output that includes a job number. If we copy it to the clipboard, we can check the status of our request by saying sq-j and then pasting the job number. The sq command responds with the status of our program. After all these column headings, there's nothing left. In fact, our program has finished already. I could get the same effect by copying my username and saying sq-u followed by my username. If you have multiple pending job requests, this will report the status of them all. Since sq indicates that our job is finished, we can enter ls again. And now we see another file named slurm-2575156.out. We can use the cat command again to view it. And there is the output from our program. Here we see the program's initial feedback for the user. We see the greetings from our different threads and our final feedback for the user. Note that since Faster has 64 cores, this program could use up to 64 threads instead of just 16. I could make this happen by using the cp command to copy my existing script to a new file named 64-script.slurm, and then editing that script, replacing all the 16s with 64s. Save those changes. I can then use sbatch again to submit this new request. If I copy the job number again, I can again use sq. There I see that this new job, OMP hello, it's pending, waiting for the resource needed to run. This will likely take a while, so rather than waste time on Faster, I'm going to cancel the job using the scancel command followed by the job number. If I then repeat the sq, I see now my job is no longer in the queue, and so it's been canceled. That concludes this SLURM OpenMP demonstration. I encourage you to watch the final presentation in this playlist where we summarize everything we've done.